Okay, welcome. Okay, two issues to discuss. One raised by Jason. Okay, so let's do that first. Jason asked, will any relations or equations be provided in the midterm? Okay, so this depends on the question. Sometimes I ask you to derive, then of course I won't tell you. And sometimes I want you to get the answer quickly and discuss the physics, then I will give you the equation. Okay, but for this course, it is very important that at least you remember how to write the first law and the second law combined. Okay, that is so important. It's called the fundamental relation of thermodynamics. Okay, so maybe let's write it here. So you need to know how to write du. Okay, this is something I guarantee I will not give you. Okay, and then you need to remember how to derive the rest. So you have deriving the rest. I mean, you need to know how to write down the corresponding form for enthalpy, for free energy, for Helmholtz function, and for Gibbs. Okay, and this should not be a problem for you because we are really using the entire chapter now to discuss Gibbs. Okay, and you should be able to find the pattern. Then from here you can extract Maxwell relation. And of course, I cannot stop you from memorizing the entire book. That is up to you. If you want to do that, that's your own freedom. But the questions are designed such that you do not need to memorize all this. Okay, but you need to at least understand, you need to at least memorize this and memorize a few very simple things like what is the natural variable for F, then you can derive everything. Okay, Jason, do you have more to add? Sorry, you have to. Okay. All right. The second thing, the second issue is the following. Let me see if the student is here. Okay. One student asked if I could grant a little bit of extension for this assignment because you have lots of deadlines. Now, because the student say he has a lot of deadlines around this week. So to be very fair, I would try my best to help. So there's a discussion. Now the original deadline is the 1st of March, and you already know the pattern for this course. The next assignment, assignment 6, will have a deadline a week after, so it will be on the 8th of March. Then on the 10th, you have the midterm. Okay. So we have a reading week as a buffer. So in principle, I can extend this for a little bit. That depends on how most people feel. Okay, so proposal, please. What is the comfortable limit for you? So if I change it, if I extend this to Friday, the 5th, will it be helpful for you, for some of you? Now the lecture hours is very precious. Please, I'm trying to help here, but you need to help me too. Is it okay? Now, if you want to, now I will say something like this. Okay, Now, if I can touch, if I don't have to touch this one, it will be good. Okay, I know these two assignments will then be very, the deadline will be very, very close. But now this is 24th only. You can plan ahead. You will get this assignment 6 very soon, tomorrow or Friday. Okay, so if I set this to the 5th, you can always submit earlier. One of you say you are not a big fan of this, but you are not opposing this, but you can always submit earlier. Okay, but at least this give a buffer to somebody who might need it. Okay, can I have your endorsement, please? No. I think you misunderstood. Sorry, maybe I didn't make it clear. Now, the email requested for an extension for the deadline of assignment 5. Okay, I propose we extend to the 5th. And assignment 6, I would be happy if we don't have to touch it. It will be the due date will be the same as the original plan, which is the 8th. So these two assignments, after this manipulation, will have very close deadline, but you have time to plan, and you can have a little bit more buffer for some of you who might need it. Okay, and assignment 6 will cover phase transition, which is definitely part of the midterm. So this is why I do not want to extend this further, even if I cannot guarantee the release of the grading of the assignment, but at least you have the chance to practice before the midterm. Okay. Okay, thank you. I think if I don't see much problem here, really. It's just for those who need it, you can get some help, a little bit of help. Okay, 4 days extension. For those who don't need it, you can just submit as planned. Okay, all right, let's do this. Okay, and then let me complete this. So this is assignment 6 will be Monday. Okay. All right, thank you. This is I will update the information on the website on Blackboard. Sorry, and I also follow up with the TA. I asked the TA to make sure assignment 1 will be returned to you by this weekend. Assignment 2 and 3 will be returned to you by next weekend. Okay, so this is all done. Any more question? If no, I want to start. Assignment 1 returned. Is it true for everybody or just for some? Okay, so I take it that assignment 1 is already graded and returned to you. And if you don't see it tomorrow, maybe there's some setting to your Blackboard. So please check. Okay, thank you very much. All right, let's continue. So this recap is very brief. I want to move forward from last lecture. And remember what we did last time. What we did last time was we showed one very important piece of information. So last lecture, we use thermodynamic potential function or thermodynamic potential to analyze phase transition. Okay, so to analyze phase transition, and more specifically, actually what we did was we used thermodynamic potential to analyze phase equilibrium. Okay, and then I put in a bit of effort to show you how to deal with variables that are extensive and or those that are intensive. And the purpose of that exercise was to let you know that you need to be very careful when you divide by the system size. Okay, which quantity will become specific quantities and which ones will remain unchanged. So this is best understood by analyzing whether a given variable is intensive or extensive. Okay, so the main result is we get this result. When you have phase 1 in equilibrium with phase 2, you have this result, which says the specific Gibbs function must be equal. Okay, when you have phase equilibrium. All right, actually this is okay. Let's look at this first. Now, sometimes when you pick up a textbook, even Blundell, if you look at Blundell, sometimes you see this result written in the capital G. Now, first, I want to say that if this is really the the extensive variable, which means if the unit is just the unit of energy, we have a problem, right? You can understand why this is a problem. This condition basically tells you, you can think of it this way. When you are in the, let's say, let's look at liquid to gas transition. When you're in the liquid phase, liquid is more stable, so the Gibbs energy, the Gibbs function of the liquid will be lower. Okay, so if you want to drive a transition, what you are doing is you are going to raise the Gibbs function of liquid until it hits the specific Gibbs function of gas, and at that point you have a phase transition. Okay, so if this is written in this form, you must check the unit. This is everywhere. This kind of writing is everywhere. So the warning is you have to always check the unit. Okay, if the unit is in energy, joule, and this is a bit of a problem because this is an extensive quantity. You do not, if you want to really trigger a phase transition, you do not simply change the system size. That's to say, now, going to the example I mentioned earlier, it will be nonsense. Suppose you're in the liquid phase, your specific Gibbs function is low. And if you want to trigger the phase transition, you want to increase it, usually by temperature, or you change the temperature and the Gibbs function, specific Gibbs function increase until you hit the value of the specific Gibbs function of the gas phase. If you don't do that, suppose you have this this kind of extensive variable, it will be very crazy because you can artificially trigger a phase transition simply by adding more liquid. You have a liquid sitting, my coffee is sitting here, and I add more coffee and suddenly it disappears, becomes vapor. That is impossible. Okay, so that is why you need to normalize somehow to the system size. Then you won't have this problem. If you add more coffee, if you normalize by the system size, this quantity is not changed at that particular condition. Okay, and to drive it across the phase transition, you have to use other quantity, for example, temperature, pressure, and so on. Okay, so if you have this kind of unit, you need to convert to specific quantity. Okay, so there will be so you will see something like for example, joule per kilogram. that will be okay. This is something we used before. When we derive this equation, we use the mass of the phase 1 and the mass of the phase 2 as a parameter to scale this kind of extensive quantity. Or most frequently, what you see is joule per mole. This is very frequent. Okay, so sometimes when you see capital letter, it's kind of a convention for some books to use lowercase to represent the specific quantity, the intensive counterpart of the same extensive quantity. But unfortunately, this is not always universally accepted. Okay, so you should always check this. Okay, so now with this, the next goal is to derive the equation describing the phase boundary. Okay, so today we want to get eventually we want to get the equation describing the phase boundary. Okay, but before that, the first step, the easier one, is to get the slope. Okay, so we get the slope first, and then we get the phase boundary. Okay, that is this business. This is the closest Clapeyron equation. Okay, so what happens here is this: if you have a phase, let's say we just look at two phases. If you have two phases, let's say phase 1 and phase 2. Now there's some phase boundary. I don't know how to draw it yet. I don't know the curve, but let's draw something generic. This is 1 and this is 2. Okay, at phase 1 and phase 2, now here you will have only the phase 1, here you will only have phase 2, and along this line you have the coexistence of phase 1 and phase 2. So this is called the coexistence curve. Or you can call this the phase boundary. Okay, the point is, along this curve, anywhere along this curve, you must have the criteria of G1 equals G2. Okay, so along this curve, anyway, you must have G1 to be the same as G2. Okay, so that's all you did. You have two neighboring phases, and along the phase boundary, you have this. Okay, let's look at it as at T, at temperature T and pressure P. Okay, so at this point, I will have G1 at this particular point on the phase diagram, G1. This looks like a 1. G1, comma, T. It has to be the same as G2. Okay, at this point. Okay, and now suppose you move a little bit to this point here by an infinitesimal amount in dt, and you get an infinitesimal increase in pressure. Okay, there, I don't really know what is the value of G1, but what I know is they must be equal to the value of G1 at P plus dP, T plus dt must be the same as the value of G2 at that point. Okay, then you can say the change of dG1 for such a small step can be regarded as the change in G2 when you move by this amount. This amount means this amount and this amount. So you move horizontally by dt and vertically by dp. Okay, what is dg? We learned last time. We learned last lecture, not long ago. We know how to write dg. This is specific quantity. These are all specific quantity, okay? For G, we didn't face much problem. The problem we faced, potential problem we faced was the Helmholtz function df. But now we don't need that. So here, you know, this is a little s dt plus little v dp. Okay, dg1 has to be the same as dg2. So what I can write is the s, so with the specific entropy of phase 1, S1 dt plus the specific volume dp has to be the same as this. Okay, and then you rearrange things, you get the slope dp dt, and that will be S2 minus S1 and V2 minus V1. Okay, let's see whether this is correct. If I move this over here, I will have V2 positive. If I move this over here, I will have S2 positive. Okay, this is correct. Okay, and then I multiply top and bottom by temperature, and this will be some kind of heat, right? This is a specific entropy multiplied by temperature. That will give me some kind of heat, which is related to latent heat. So I use lowercase l, and then T V2 minus V1. Okay, so this is specific latent heat. Okay, so now if I multiply by the system size, for this equation at the top and bottom, I can do that. You see, this is a specific quantity and this is a specific quantity. If I multiply by the system size for the top and the bottom, I will be able to get the latent heat, not latent heat per mole, not latent heat per kilogram, but latent heat given in joule, divided by the temperature and the volume difference. Okay, and this equation is the Clausius-Clapeyron equation. Okay, so this is what we want. I will call it CC, easier. Okay, so what is the feature here? Now, I want to stop at this page. What is the next page? Okay, I want to stop here for a bit to look at this equation. Now, look at here. From here, I already predict something. I predict the entropy has to jump and the volume has to jump. Okay, and these are the key features of first order transition. Again, right? So I already mentioned last time. Last time you already saw entropy would jump, and I told you the volume would jump. Okay, so these equations are consistent with the fact that both the entropy and the volume can jump. Okay, of course, you have special cases. For example, if the entropy change is very tiny, you have a very small slope. Okay, and just remember this, when you look at the phase diagram for example, H2O, you can appreciate this a little bit. Why the slope is steep for liquid to solid phase transition? Why is it more gentle for liquid to gas, and so on? Okay, these are simply captured by this. Okay, so here from this equation, the CC equation gives the feature of the first order transition. Okay, what are there? You have volume jump, and entropy jumps. Where do they jump? They jump at the phase transition temperature. Sorry, actually it doesn't need to be temperature. It can be phase transition pressure, but you are more familiar with temperature. I would say at phase boundary. Okay. And first order transition, because of this, because the entropy jump, another way to look at first order transition is this is a phase transition that will involve latent heat, right? Why? Because latent heat is this term here, right? So if the entropy is continuous, it doesn't show a jump, but let's say the entropy of phase 1 meets the entropy of phase 2 at the phase transition temperature, doesn't show a discontinuity, then there will be no latent heat. Okay, so another way to look at this is first order transition in both latent heat. Okay, so a generic one look like this. Sorry, let's see if I should have a. This is a generic diagram, something that looks like this. Okay, this is pressure, temperature. We will come back to here later. But I can draw something very simple. So here, usually it looks something like this. And then with a critical point here. Okay, this is called the triple point because this is where three phases meet. So you have your solid phase, liquid phase, and you have your gas phase. They all meet at this point. Okay, at this point, you have the specific Gibbs function of all three phases to be the same. Okay, but now, here, I just want to focus on the slope. Remember, the CC equation tells you only the slope. So this tells you the slope on the PT diagram, Okay, so the slope, this slope, dp dt, is, let's reproduce it here, is related to this. Okay, and another reminder is this. When you write it like this latent heat is the latent heat when you change from phase 1 to phase 2. Okay, if you have the other way around, the latent heat, of course, will acquire a minus sign. Okay, so this one is phase change, phase changes from 1 to 2. Just be consistent with this guy. Okay, and this is important because we want to discuss the sign, right? You can see the slope, the local slope at least, is always positive on this diagram. Okay, and I say on this diagram because for water you have this slope will be slightly, it will be negative. Okay, now the reason here is this. Why do you have a much steeper slope here? The reason you have much steeper slope, so much steeper slope for liquid to solid transition, because as we already discussed last time, the particle-particle distance in liquid and the particle-particle distance in solid are not very different. So the change in volume, there will be some change, but the change in volume will be small. Okay, because the change of volume is small. How do I what do I mean by small? Small compared with what? Small compared with when you undergo the transition like this from gas to liquid. Okay, so for water, you have anomalous expansion. So you have a slope that goes like that. So when you, so this is for most cases. So for most cases, dp dt is positive, except for water. For the phase boundary of liquid water and solid water, which means ice, that's because the volume shrinks. So H2O shrinks slightly. When you melt ice. Okay, and this is also why the water is dangerous. You have a very good recipe to break your glass by knowing this piece of physics. Okay, and then another quick comment is this: when you go from liquid to gas, volume will expand very, very quickly. Do you know the expansion ratio? Let's say I take 1 liter of liquid. What is the expansion ratio? Let's say a typical gas. That doesn't need to be very precise. You take 1 liter of let's say liquid oxygen, and when it expands into gas, what is the expansion ratio? Do you have this number in mind? Can you guess? Factor of 10, 100, 1000, or what? Okay, not a bad guess. More? Okay, this expansion factor is several hundred, close to 1000. So this is why it's very dangerous to take liquid nitrogen and go inside a lift. I have seen students doing this in our department. They take liquid nitrogen. The liquid nitrogen looks like 3 liters to me. And then when they enter the lift, I always want to go out, because the reason is very simple. If you take the lift from ground floor to 3rd floor and the lift is broken. Then you have this several liters of liquid nitrogen that can expand slowly. It depends on what time this happens. If it happens very late in the night, you might be in trouble. Okay, and you displace oxygen and you have really big trouble. And that's why I really do not like to see people taking liquid nitrogen inside the lift. In many places, this is not allowed. This is actually very dangerous. I've seen cases like this a few times. So this is something you should at least keep in mind after taking this course. Okay, so we know the slope. Okay, this question is interesting. How do I know they are taking liquid nitrogen? It's very simple. You will see when they take liquid nitrogen first, it's very cold. The liquid nitrogen temperature is 77 Kelvin. So you always see some, it looks very cool. It's a bit like some spatial effects. And the container always have this steam coming out. It's not water steam, but it's constantly boiling, right? And that is a good sign. And then you will see condensation around the container because it's so cold. And most likely you will see liquid nitrogen because we don't really have other coolant that is readily available like this. For example, another coolant will be liquid helium. Liquid helium will have the same problem, but liquid helium is so expensive. You won't take it like this. You have a very spatial transport jewel, spatial container to transport it. Okay, and then there are other coolant that are useful. For example, liquid argon is also similar. Liquid argon, the boiling point is similar to liquid nitrogen, a bit higher. But argon is so expensive and you won't do it like this. Okay, so liquid nitrogen is very conventional. You have so much nitrogen in the air, you can, it's a great substance for quick cooling. And this is why we use it so much. In hospital, you see a lot. You see lots of liquid nitrogen. They have their own liquid nitrogen tower to do that. Okay, so don't worry. If you see it, you know you have it, or you just ask. Just ask what is this very fancy material in the bucket. They will tell you. Okay, so now you know the slope. Can we find, you know the slope, dp/dt. Can we find the explicit form of this curve? Pressure versus temperature for the phase boundary. Okay, and to do that, you need to integrate. And when you want to integrate things like this, you will need some assumption. Okay, and the easiest one is to look at liquid and gas. Liquid and gas. This is the assumptions are easier to handle. Why? Because we can treat the gas phase to be an ideal gas. Okay, so if you do that, you can actually get this equation quite quickly, and that will give you some insight. Okay, if you want to get this, you need to integrate. So you need to integrate. Need to integrate the CC equation with some assumption. What are our assumptions? Assumptions. There are a few. Huh? So so I'm going to so we are going to look at liquid to gas transition. That's the easiest. You know why. Okay, the rest is not that easy because you need to really look at the temperature or pressure dependence of all these quantities. So those are, in principle, you can do, but you need to know more about the microscopic details of the system. Okay, particularly if you involve the solid phase. A solid phase is very complicated. It depends on the structure of the material and how you model the temperature dependence of volume and pressure dependence of volume. So it's not as straightforward as looking at the gas. I guess it's simple because why? The assumption we can do is we can take the gas phase to be an ideal gas. Okay, and then and the other thing, this is not quite an assumption, this is really a reality. I already mentioned, when you have liquid nitrogen, you have a large expansion. Okay, so in this case, you can take delta V, which is a change of volume, to be pretty much the volume of the gas phase. Because this change is factor of several hundred, so you don't need to worry about the tiny offset. Okay, so from here, there are further assumptions, but now let's look at this equation. This equation already become simpler. Right, so okay, let's write this. This is T delta V. Okay, this is all in extensive quantities. So if I put all this assumption in, I will first have the V to be the V of the gas phase. This is excellent. I do not need to worry about the liquid phase, the volume of the liquid. It disappears. Okay, and the second assumption kicks in. So this is assumption 2, actually. And this is assumption 1. And now I have something even better. I can write it in terms of pressure by using the ideal gas law. Right, so from here, I just simply change to the ideal gas law, and I reach here. Okay, but that is not done yet, because now I get stuck here unless I know how to model my latent heat. Okay, so I know how to model the volume of the gas by using the ideal gas law, but still I need more. Okay, what are the steps after? So the steps after will be number 3. We need to say something about this L. So the simplest one is to look at L, which is independent of temperature. Okay, this is not too bad. And the mathematics is very simple, so I'm going to do this. Or you can also, so I will do or for the next one people do is they assume the heat capacity of the two phases to be constant. So this is the heat capacity of the two phases are constant. Okay, I will do this. I will do the easier one, and you will do this in your assignment. Okay, so number 3, so we already get to here. So number 3, if we proceed from here, I can write it here first, and then I will go down. No, I changed my mind. So 3, so with 3, I can integrate like this. I can integrate dP, I can move the pressure to here. And because L is independent of temperature, I can move it out like this. Then I can integrate 1 over T squared dt. Okay, and here you know when you integrate this, you get a log, natural log. and this will still give you some power. The end result is you get pressure, and this is your M. You want to get this. The end result, only 2 more lines, you can fill in the gap yourself. You get, the key is you get a log. For this discussion, I want to extract this exponential behavior. Okay, and this will be, we can write it in a slightly different way. If you just manipulate this integral, you get this result. That tells you how your pressure varies as a function of temperature for the liquid to gas phase transition boundary. Okay, so I want to change it to L over NA. Now this is gas constant. Right? Gas constant is Avogadro's number multiplied by Boltzmann constant. I want this Boltzmann constant here. Okay, so I simply rewrite it this way. Why do I want to do that? The reason I want to do that is hopefully you identify this as a Boltzmann factor. So this exponential here is this is a Boltzmann factor. Exponential of some energy scale divided by thermal energy. So this is a Boltzmann factor. If you don't worry. I hope you would, because you should have seen this before. If you don't, I guarantee you that you will see plenty of Boltzmann factors for the later half of the course. Okay. And why do I want to extract this Boltzmann factor? Because I want to interpret this as some kind of probability. Okay, this is some kind of energy barrier, right? So this is how we learn Boltzmann factor. Okay, so you can interpret this as this factor as proportional to the probability of a molecule being excited from the liquid to the gas phase. And what is this energy barrier? This energy barrier is the energy cost you have to pay to turn yourself from liquid into gas, and this is the latent heat per particle. Okay, so actually the latent heat per mole, there's this is Na, not M. Okay, so this interpretation is this is proportional. Proportional. Sorry, I will just write it as probability. So this is really the probability of a molecule being excited from liquid to gas over some energy cost. This is the energy over an energy barrier, L over Na. Okay, so this is what I want to say. Okay, this slide we don't need. Okay, so now let's look at some phase diagram and take a break later. Okay, I present here two phase diagrams. One is phase diagram of water, which we have been talking about. Actually, I want to start from carbon dioxide. And this is a typical one. You see, everything has a positive local slope. And here, this is a triple point. Now, the key here is to look at where is the atmospheric pressure. Okay, so this triple point happens at about here, and the one 1 bar, 1 atmospheric pressure is labeled here for you. Okay, and that's why for carbon dioxide, you can, at 1 atmospheric pressure, that is to say, if you do this experiment in the lab, you open to the atmosphere, then you can actually have formation of dry ice if you cool it down. Okay, or another way to say that is if you take dry ice, you put in your container to cool your ice cream, you don't end up having a lot of water because dry ice will just turn into gas directly. Okay, because you are at 1 bar. Unless you increase pressure, otherwise you miss the liquid phase altogether. Okay, and now if you look at water, this is something I promised you earlier. I promised you that this slope for the liquid solid phase boundary would be a little bit different, and this is why this is different. Okay, another thing probably we should know is 1 bar is here, 1 atmospheric pressure is here, ambient pressure is here. So if you draw a horizontal line, you will know your boiling point. So your boiling point will be here, which is, you know, from primary school is 100 degrees Celsius. Okay, and here this is 0 degrees Celsius. And the triple point is slightly above 0 degree. And why? This is shown in this phase diagram. Okay, the triple point is 0.01 degrees Celsius, 0.01 K. We already wrote this before. Okay, and because this slope is positive, when you go to mountain, the pressure drops, right? When you move up the atmosphere, pressure drops, and that's why your boiling can happen at lower temperature. Okay, and if you believe 100 degrees is what you need to kill all the bacteria, all the germs, then good luck. If you go to mountain, you go and go camping there, and you want to try to sanitize your food by cooking it in water, then you need to be careful. The temperature will be lower. Okay, and this is actually we have similar experience before. If you have the helium phase diagram, everything will be at much lower temperature, and you will see something similar to the helium. And there, helium, the boiling point of helium is something we use as a way to cool down materials. Right? So we, how do we want to cool a piece of material, a piece of superconductor down to very low temperature? Liquid helium is something we use very quickly. And the slope looks a little bit like this too. Liquid helium to gas helium looks like this too, but there will be some complication there. So one trick to gain a little bit of temperature, to cool down material a little bit more, is by pumping, by reduce the pressure of the gas, and that will bring the boiling point down, and you can do your experiment for a little bit more, a little bit lower temperature. Okay, so now there are some questions, but I want to finish this, take the break and look at the questions. Don't assume this is just like this, okay? Now look, this is the phase diagram of water. I told you solid state is very complicated and interesting. Now this is another phase diagram which is more extended, which means I extend to a much greater pressure range and temperature range. And this is the phase diagram of water. So what you have seen was somewhere here. Okay, and you can see ice is actually very, very rich. If you are someone who is interested in solid state or different crystal structure, you can do tons of experiment here. You can go to so many different phases, and they will have different structure, and these are called the polymorph. Something a term I introduced last lecture. Okay, so let's take a break and come back at 1:35. Okay, so where were we before the break? Okay, we look at this phase diagram, which is very complicated. I think the message here, the message to deliver here is this is what we can do at this level of the course. And if you want to get this kind of phase diagram, you need a lot of knowledge about your system. So that will probably, most likely, involve a lot of experimental data. Okay, so there's for your reference, actually for your amusement. You see, you can see the structure here. Sometimes they label the structure hexagonal. What is the meaning of this? What is the orthorhombic? That is really the crystal structure. All right, so I need to discuss this order of transition business. What do I mean by order of transition? Okay, and this is actually something very old, and but it's still useful. We probably don't use it much today, but it's it has now, once you learn thermodynamics up to this point, this discussion really makes sense. Okay, so this is actually due to Ehrenfest. This is called Ehrenfest classification. Okay, so in word, the order, what do I mean by first, second, or higher order? So the order of a phase transition is the order of the lowest differential of G, the Gibbs function that shows a discontinuity. A discontinuity. Okay, discontinuity at the phase transition. Okay, everything should make sense now. Why? Because you already learned how to deal with Maxwell relations. So you know how to write all these differential to higher order. So the first order will be very simple. Okay, you have the form of dg. Okay, differential form of Gibbs function. So the entropy is the first order differential. Why? Because this is simply given by this. Okay, and first order transition requires the first order of the differential to show a discontinuity. And that is why you have the jump in the entropy. Okay, in fact, if you look at the volume, you also have a jump here. This is plus. This is with respect to pressure and T. Okay, this comes from the differential form of Gibbs function. So from here. Okay, so from here you write dg, you can identify these two differential. Okay, and this must shows this continuity at the phase boundary. Okay, and therefore for second order phase transition, second order. Now this is the first order, right? So for the second order, you must expect the discontinuity to happen at the second order. And therefore, for the first order differential of the second order phase transition, namely entropy and volume, you do not have a jump. So this kind of phase transition is very interesting for second order phase transition. You have a phase transition, but your volume doesn't change. I will show you a figure later. At the phase transition boundary, your volume is continuous. It doesn't need to be differentiable, but is continuous. When you have a jump, this point is not differentiable. Okay, and that's why when you evaluate the next differential for the first order transition, you have a anomaly which shoot to infinity, right? Because that point is not differentiable. And that is the heat capacity. Okay, so for us, this is a very important stuff, because we can do experiment again to figure out which order of transition do we have. Okay, so let's have a look at the next figure. This is what we learned for this chapter. Okay, this is from Blundell and Blundell. And again, I would like to interpret this as the specific quantity G, lowercase g. So this is given in joule per mole. Okay, so I can, for example, I can see this as liquid to gas phase. Okay, so if I'm in the gas phase, let's say, suppose I have a way to calculate the specific Gibbs function. I will get something like this maybe for the gas, and for the liquid phase, I will get something that goes down. Okay, so I will color code this for you. This is the green. The other one is the blue. Okay, so the phase that has the lower specific Gibbs function will win. That is a stable phase. Okay, and at the phase transition, they meet. These two values meet. Okay, this is what we actually, the top panel is what we have developed so far. So you have liquid to gas, and the first order differential shows a jump. Okay, this is volume. I can also do the same with the entropy. And if I take further derivative of the entropy, I will be able to calculate the heat capacity. And this is what I showed in the last lecture. Okay, and if you have a second order phase transition, for example, this can happen when you have some certain structural phase transition. This can be structural phase 2, structural phase 1, and you have a Gibbs function that has no feature. Okay, so here, when you take the first derivative, you see a kink. Yeah. But this is not a jump. Okay, so everything kind of get displaced by one column if you like. And if you have a kink and you take derivative, you get something that looks like this curve, but it happens in the second order differential. Okay, so the next table will tell you what we have. Okay, so according to this, we know if you have first order transition, the discontinuity will appear in entropy and volume. So this is what we have. Okay, this is from Akin. He used specific quantity. So you have specific, it doesn't matter. So you have a jump in the specific entropy and specific volume. And for the second order, you have a jump in the heat capacity, and this is what we can measure. And you have a jump in the thermal expansion. This is also something we can measure. And you also have a jump in the compressibility. So the compressibility will change at the phase transition. Okay, this is also something we can measure. Okay, so and if you want to go to higher, you can keep going, but usually the point is this: if you have a first order transition, we call this discontinuous phase transition because everything happens very, very dramatically at the phase transition temperature. Okay, so you have a large volume jump. Whereas for second order or higher order phase transition, we call it the continuous phase transition because the phase transition really looks like a continuous evolution from one phase to the other. And you have all this discontinuity only when you examine the higher order derivatives. Okay, so this is what we can say about this order of phase transition. And to do more, you need to learn more theory about phase transition. For example, you can have Landau theory of phase transition. There's a theory that describes how to analyze phase transition, extract the order parameter of the phase transition, and there's a huge subject. As I said, you can find the entire book written on this kind of physics. Okay. And before we close this chapter, I want to also very quickly discuss how do we know which phase to pick. I already told you this is, I already give you this picture. Okay, if you have two phase like this, the one with the lower specific Gibbs function will win, will be the stable phase. But here, let's see if we can gain some insight by already using the knowledge we developed so far. Okay, so what we want to compare, which phase to pick, in principle, we need to suppose you are able to calculate a specific Gibbs function. So I'm going to use capital G, but what I mean is this is Gibbs normalized by per mole or per kilogram. Okay, so I'm also going to look at only a pure substance for a pure substance. I'm going to use solid and gas. I don't want to use liquid because liquid is a little bit harder to model. And for this qualitative analysis, qualitative argument anyway, there's no much advantage to add this complication. So I'm going to look at G versus T, let's say, for solid and gas. Okay, this is quite nice already because our aim is to explain why we have different phases at different temperature. Okay, so if I have if I plot G versus T here. Okay, let's remind ourselves what is G. Okay, so G is the internal energy minus temperature times the entropy plus PV. Okay, now here you want to ask yourself, if I really want to stabilize a particular phase, I really want to gain advantage by minimizing G, right? So if I compare two phases, this is what I want. Okay, so schematically, let me draw something first. So I put the 0 here. Let's look at this term one by one and only use the gas and solid to construct the argument. So in a solid, U is usually very, very large. This is the internal energy. This internal energy is due to the interaction between the atoms. Okay, and the internal energy can also come from other form, but this is the dominant form in solid. Okay, so this is due to the interaction. Due to the interaction between atoms. So this is called the cohesive energy. Cohesive energy. Okay, so in solid, it's usually large and negative. This is large because the atoms are close together, the interaction is large, and you want to what did I say? This is large and negative in solids because of the close proximity. Okay, suppose you do this kind of calculation, you find something large and negative for solid. And in comparison, when you have gas, you have something a lot smaller, orders of magnitude smaller in gas. So U is for gas, it is orders of magnitude smaller. So for gas, you will be somewhere here. So I will do this as gas and this solid. As I say, I don't want to worry about liquid. Okay, let's say you do some first principle calculation. You know everything about your system. You know everything about the structure of your solid. You can do the calculation and estimate the U. And order of magnitude wise, you have a picture like this. And now you want to ask yourself, what is the effect of other terms? Now the effect of the second term is not relevant at low temperature because T approaches 0. So you start somewhere here. Okay, and you need to ask yourself, how is it possible that I can trigger a phase transition into the gas phase? Right? If nothing happens and nothing will change as a function of temperature, I would just have maybe I will have a little bit of entropy for both. Then I will have some slope, right? Both of them will change like that. Okay, the reason we can even have a chance to stabilize the gas phase is precisely because of the second term in this equation. Okay, so solid has low entropy compared with the gas because solid has less freedom to explore. So solid has lower entropy compared with the gas. Okay, here we are only talking about these two. Okay, and gas has high entropy, and you want to win. And the way you win is to take advantage of the high temperature because this amplify your S. Okay, at the beginning, even though in your calculation, you can estimate the entropy to be some value. Let's assume we can take some realistic model and get some realistic entropy. If you want to gain order of magnitude advantage, that is very difficult at low temperature. Okay, so that's why the high temperature helps, and you have a term which is much lower compared with solid at high temperature. Okay, and then of course you need to consider the PV term as well. Now, when you look at PV term, all this, of course, will requires you to look at the detail and put in the numbers carefully. But if you just look at the temperature, look at the term with volume, this is actually a rather bad news for gas because gas has very high volume, right? The expansion factor is several hundred compared with solid. So this term, if I just look at this, I would say this is probably bad news. But in fact, you can stabilize the gas phase because you are helped by the second term. Okay, so large volume in gas compared with solid. So this is bad news for stabilization, for stability, for phase stability, but the TS term might help. Okay, so put all this in. You can kind of imagine maybe you have a curve that looks like this, and a curve that goes down, but a little bit slower. So this is where you trigger the phase transition, and this will be your phase transition temperature. Okay, so this is solid. So solid, I make it dash line for you. Okay, so at low temperature, you stabilize a solid phase. At high temperature, gas wind. Okay, so this is actually some computational scientists do this on daily basis. This is from calculation. You see, this is again in the unit of joule per mole. And with some data and some computational power, they are able to come up with this kind of calculations. And you see this quite often, actually, particularly if you want to predict a new structure. What do? You calculate the Gibbs function for all the structures. You use your best assumptions you can have, and you calculate that as a function of the parameter you want, and see whether you can trigger a phase transition. So this is from a textbook, not our textbook. I found it on from Podesta. So here, this is what he tried to calculate, and is qualitatively similar to what I mentioned to you. Now, because if you don't put in numbers, so here he put in numbers, you cannot really argue too much about the relative size of the second and the third term. But once you put in number, he calculated this for potassium, and he can predict a liquid to gas transition and a solid to liquid transition at a temperature which is not too crazy. Okay, so here you don't really care about this point anymore because you will not see it. This is not the minimum. So you always care about the lower space. Okay, so at least from the knowledge you learn from this chapter, it would be nice if when you see figures like this, you won't be too intimidated by this. There are a lot of figures like this in the literature, actually. People really care a lot about phase transition. Okay, so this is what I want to cover for this chapter. Okay, we have 10 minutes left. I already posted the draft of chapter 7. So I'm going to talk about this a little bit. So this is chapter 7. The title is this. Is beyond a simple PV system. So we have been talking about PV systems up to now, all kind of thermodynamic functions developed for PV system. And now in this chapter, I want to, this is the last chapter of thermodynamics. So very soon we are going to switch to statistical mechanics. So this is a good place to show you that you can do thermodynamics on other systems beyond a simple PV system. Okay, the first one the first thing we can relax is to open our system. We have been talking about a system with a constant number of particles, n. Okay, we can actually open the system and see what happened. And I want to also talk about some elastic rod. Okay. And finally, I want to talk about magnets, or more precisely, a paramagnet. These are very, very interesting thermodynamic systems. Okay, in the note, I think I put open system last, but I would like to switch this here because this is kind of a convenient place after learning phase transition. Okay, so if I start with an open system, what is my first law become? How do I write my first law? Look, how do I change the internal energy? How do I increase the internal energy? We know we can do it in several ways. First, we can add heat, and that is the TDS term. And second, we can do PV work. So this open system is still PV, but it's not a simple PV. Okay, we can do work. And finally, we can bring in particle. Okay, so if my particle that I add to my thermodynamic system contains some energy per particle, which I call mu, then I change the internal energy. Okay, so this mu is called the chemical potential. Do you hear some noise from my background? Okay, so U here is, when you write it this way, you know, you can write U as a function of S, V, and N, like this. Okay, so I generalize it to this form. Okay, if I write it this way, then I can identify the partial derivatives I want. Okay, and the rest are actually simple. But the new one you bring in takes the meaning of partial derivative of U divided by partial U with respect to N, and you keep S and V constant. That's it. Okay, so once we have an open system, this will be the first and the second law combined. This is how we write it. Okay, and by now you should already know that you sometimes don't want entropy. You would rather control the temperature. Then you can have, for example, you can have Helmholtz function. F will be U minus TS. This is still the same, but now U, when you do the differential du, you have this term. You introduce this term, and therefore your df will also have an additional term. Okay, I will just write it without deriving it again. You have seen it. This is a plus mu dn. Okay, so here you can, just like before, you can identify mu like this too. So this depends on the constraint, depends on what is convenient for you. So this is TV. Okay, you can do the same with the Gibbs, do the same, and you get mu to be like that, to be written like this, T and P. Okay, what is the role of this mu? What is this mysterious mu doing? Okay, we asked the same question before. We asked the question we asked earlier was, what is the role of pressure? What is the role of temperature? Now I want to ask the same question, what is the role of mu? Okay. So I'm going to discuss condition, a spatial condition. I'm going to discuss systems that can exchange heat and particle. Okay, I do not want to worry about volume change. This is something you have seen in assignment 4. So in assignment 4, you look at a similar problem, and now I want to extend it a bit. Okay, so the system will be something like this. I'm going to draw two systems, subsystem 1 and 2. And then I can exchange particle. I can exchange heat. And otherwise, I want to close this to the outside wall. So this is an adiabatic wall. And this is 1 and this is 2. Okay, so I do not allow this partition to move. I do not allow this container to change size. So dV is 0. Okay, how do you answer this kind of question? The way to do this, again, is to use the second law. Okay, so from here, we know how to write du. Okay, I'm going to first write ds for you. So ds is du over t plus pdv over t minus mu over t dn. Okay? And from here we can, so from here we know this partial derivative, keeping u and v constant, will be minus mu over t. Okay, the system, the two subsystem 1 and 2 combined is a system which is close to the outside world. So I will have n1 plus n2 to be a constant. Okay, this constant is n. So if I do the differential, I will have dn1 plus n2 is 0. So dn1 is minus dn2. Okay, and now I will write the total entropy. The total entropy change cannot decrease. And what is the ds total? That will be the change of entropy for system 1 plus the change of entropy for system 2. Identical formula. It's just before we treat one of these as reservoir and one as a system, and now I just call them system 1, system 2. Okay, and then you look at this. You look at this expression here, and you write it for 1 and 2. So you have so here you have du1 t1 minus dv is 0, so I don't care anymore, minus mu1 t1 dn1 plus du u2 t2 minus a, and my mu has a long tail, you see, mu, don't be confused with u. So mu2 t2 dn2. Okay, so this is the left hand side, and I'm going to bring everything with everything with du together. So I will have 1 over t1 minus 1 over t2 du1 minus mu1 over T1 minus mu1 over T1 minus mu2 over T2 dn1. Okay, so what have I done here? What I've done is I have used the fact that dn1, this equality, I use dn1 is minus dn2. Okay, and then I have du1 is minus du2. Okay, so if I have some exchange of the internal energy, it can only go to the other side of the system. Likewise with the change of the particle. Okay, I'm nearly done. Just a few more minutes. Sorry. Okay, so now this has to be positive. This has to be positive. Okay, I hope I didn't make any mistake here. Should be okay. So the next thing I want to extract is this. Even if, listen carefully, my logic here is this. I'm going to set T1 to be the same as T2, just for simplicity to get the meaning of mu out directly. Okay, so even if I have T1 equals T2, I need to still look at the relative size of mu1 and mu2. Okay, so if I set mu1, T1 equals T2, if the particle is still moving, even if this is the case, I need to respect this inequality. Okay, so first term will be gone. I don't need to worry about this. And I can look at the second term. And for this to be positive, I need to look at the sign of this term and this term in front. Okay, if I want dn1 to be positive, if dn1 is positive, then I will need, then mu2 has to be greater than mu1. Okay, that is to say, now what is the meaning of dn1 to be positive? dn1 to be positive means system 1 gain particle. So this means system 1 gains particle. And how can it be true? This can be true only if my mu2 is greater than mu1. Okay, so that is kind of the meaning of chemical potential. There's a chemical potential difference, and that drives the particle flow. Okay, and at equilibrium, as you can already guess, what happens at equilibrium? At equilibrium, your mu2 will be the same as mu1. Okay, and this is similar to what you had before. When you have thermal equilibrium, you have T1 equals T2. When you have mechanical equilibrium, you have P1 equals P2. I don't discuss this because my volume cannot change. And if I have diffusive equilibrium, then I would demand my mu to be the same. Okay, so the message is that the flow of the particle is driven by the difference in the chemical potential. Okay, I think this is a good point to stop. And next lecture, I will continue from here.